Hello, this is Pam Hoffman, Everyday Spacer.
I'm Jeff Miller, 2049 Outfitters.
At Everyday Spacer, we show regular folks how to personally and directly participate in space exploration, science, and astronomy. We're here on Friday nights at 9 p.m. Pacific Time, 12 midnight Eastern Time, and 3 p.m. on Saturday in Queensland, Australia. We're broadcasting live from Thousand Oaks, California. Here's you.
Okay, tonight, help us welcome Jeff Greason. We'll be back in 8.3 seconds.
Link to that book in the comments this time.
Okay, and Sergey.
Welcome, Alex. This is Alex. I am Alex.
I'm Alex. Okay, there we go. Hi, Alex. Jamie Becker.
Welcome
Hi,
back.
Jamie.
Yep.
And
oh, good.
Peter.
Spaced out to me.
Okay. Jeff Greason.
Greason.
I'm sorry, Jeff.
We both did it.
Yep. Jeff Greason is a commercial space innovator with over 25 years of experience in all aspects of commercial space transportation industry. He's a chief technologist of Electric Sky, where he has invented technologies for the transmission of wireless power to aircraft and spacecraft, and it's used for propulsion and other purposes. Through work with the Tau Zero Foundation and Interstellar Research Group, he has developed a number of technologies for advanced space propulsion applicable to interstellar flight and solar system exploration. He has given a number of speeches on strategies for expanding human presence out into the solar system and beyond.
And we got one more. Scott's here. Thanks for joining us, Scott. We really appreciate you being here. And thanks for Jeff, too. All right. We've known Jeff Greason for quite a while now, mostly during his XCOR days. You came here to listen to Jeff, though, so we're going to let him talk about anything he wants to from his extensive bio. We only gave you a brief look at it. And so, yeah, okay, one more. Dawn's here. Hi. Hi, Dawn. So, Jeff, tell us about yourself and share with us what is important and inspiring to you.
Well, briefly, I've had a very strange background for being in the space world. I don't ever remember a time when I didn't expect to live in a spacefaring society. In fact, we're well behind where I hoped we'd be when I was a kid. But I didn't think that meant I had to go out and get in the rocket business. My love was electronics, and I figured there'd be plenty of jobs for electrical engineers in space. So I went on and had that career and, got that degree and spent the first 9 or 10 years of my professional life at Intel working on developing chips and chip making technologies. Although it turned out to be a great training ground because that was my exposure, kind of baptism of fire for how you do technology road mapping and how you work on, how do you develop products that are where you're depending on 3 years from now, there being technologies that today you don't know how to do.
Wow.
But, and then I eventually decided to change careers and get into the nascent space business back when, we could fit the entire commercial space industry in a small hotel in Phoenix.
Yes.
But as for why I do this, I mean, I've been asked that question many, many times over the years, so it always comes out as some different flavor of the same thing. It's really two things. Values are subjective, but I value a human society that embraces personal liberty and change and improvement. I don't want to live in a static bureaucratic empire where nothing ever changes for 2,000 years. And everybody is, a serf of somebody else. And I think that kind of society can only exist when people understand that life is a positive sum game and not a zero sum game. It's not just about spreading around pieces of pie. It's making new pie. And I think a frontier and the perception of there being a frontier is important in sustaining that belief. Now, you can argue whether it's in reality necessary. I don't necessarily make that argument, but I think when there is a frontier, belief in the zero-sum game just seems silly, and so there's always people arguing that if somebody has something, it must be because they took it from you and you should just go take it back.
Mm-hmm.
But in periods where there's a frontier, I think those beliefs don't flourish, and therefore society does flourish, and space is our final frontier, so we should go get it.
I think we have a bunch of frontiers. We have a question for you too. So
okay, let me finish this little bit, and then I will open that over for questions. The other part of it is, if you look at the life cycle of civilizations over about the last 4,000 years, the failures are random. They're not systematic. It's kind of like a radioactive half-life curve. The probability of a civilization collapsing in a given year is independent of how many years it's been around. But the mean time between failure is about 400 years. And right now, our technology for communication and transportation across the planet are so good that we essentially have one interlocking global civilization, which means when, not if, when we have a civilizational collapse, it might be global. And most of the time when a civilization collapses, it's a local event, and it's not that big of a deal. The neighboring civilization moves in, and maybe it's tough for a few years, but life goes on. But if you look at things like the Bronze Age collapse, where it was regional, and lots of civilizations in the area went down at the same time, that was very bad news. Literacy was lost. The economy collapsed for hundreds of years. It was very bad news. We don't know what a global collapse would be like, and I'd really rather not find out. And the only insulation or insurance you can have against that is to get back to the historical norm, where outposts of human civilization are separated by enough time and expense and distance that they have to be somewhat independent of each other. That way, when one of them goes down, the other one, the civilization as a whole is not lost. You don't forget how to do all these things. Life goes on. And so the only way to do that is to spread humanity across more than one planet, because our technology right now is so good that one planet's not big enough to have more than one outpost of human civilization. So that's part of the reason I do this. And that's also part of the reason why I work on advanced space propulsion and interstellar flight, because even though I don't expect to see that enterprise come to fruition real soon, changing people's minds that isn't just a thing that could never happen, making them realize that's a thing that can happen and it will happen if we persist, helps them to realize that. And when we get out in the solar system, that's the beginning of the journey, not the end of the journey. Okay, so now with the end of my soapbox rant, and if we still have a question, I can take it, but I don't see it up anymore.
Oh yeah, Peter R just said, "Did you watch the SpaceX launch this week?" And that was
heck yeah. No, I am. The space industry is not such a big place. Even though Elon has climbed far beyond all the rest of us. I remember when Elon was the new kid on the block, and coming up to us to do testing. So we don't all get along, but and I can quibble with some of the things that maybe Elon does, but I wish only for his success and for the success of the thousands of people who work at SpaceX and Gwen Shotwell, who actually runs the day-to-day operations over there. And I'm pulling for him. But the people, how do I put this? People chat about the wrong things. It used to be said as a kind of a truism that in military affairs, amateurs discuss tactics and professionals discuss logistics. In space transportation, amateurs discuss technology and professionals discuss markets. Is there enough traffic? If the technical issues with Starship, whatever they may be, will be worked out in the fullness of time, unless they run out of money, which they're not going to. So it will eventually get the technical issues worked out. If there are hundreds of paying customers per year for Starship, it will be cheap. Mm-hmm. Are there hundreds of paying customers a year for a vehicle as big as Starship? We don't know. I don't know. Gwen doesn't know. Elon doesn't know. The only way to find out is to build it and find out. So that's what they're doing, and I couldn't be happier.
Yeah, it seems like it's following the whole business with planes and airlines. It's kind of the same thing. You kind of get the rich people buying the tickets at the beginning.
It is, but from time to time in the history of transportation, people notice that the equations tell you it would be more economical if you built a bigger ship.
Mm-hmm.
And sometimes you catch things just right. You build the DC-3 just in time for World War II, and people order 10,000 of them and they get cheap.
Mm-hmm.
And sometimes you build the Spruce Goose and it never flies, or you build the Great Eastern and there's no market for it.
Oh yeah,
you can't predict those things, that because market surveys for markets that don't exist yet are not really worth the paper they're printed on.
Mm-hmm.
So the only way sometimes to find out is you roll the dice and you introduce the product and you find out if it works. And that's what they're doing, and I hope it works. And I spend part of my days saying, okay, if it doesn't work, not technically, if it doesn't work because there isn't the market for that much traffic right now, what else could we do?
Yep. Yeah, because he's building something, so it's going to be useful for something, even if it's not useful for what he wants it to be. So
I hope so.
Yeah,
and I think the chances are fairly good. But I haven't spent the last 30 years just sitting around waiting for Elon. So
you were there before him.
I was.
I mean,
in a very small way.
Yeah, we met, although you don't remember us, but we definitely remember you in the old Space Access Society days, where you were one of the few guys who were bending metal instead of just complaining about lack of commercial space. You guys were bending metal.
Yep.
Yes.
You, Carmack, Powell,
which was wonderful.
Maston.
I think of those times as the doldrums, and you guys came along and had the T card, and I was like, "Oh my God, this is amazing."
Yeah. And
no, I think we did some good. I think we, even though the company, is no more, and obviously we didn't achieve the business objectives that we hoped for. Mm-hmm. I do think we contributed to changing people's minds about what you could and couldn't do. Mm-hmm. I was sometimes told we made it look too easy. So instead of buying rockets from us, everybody said, well, if they can do it, we can do it too. Which isn't the worst outcome. And also, at the time we started, you really couldn't find anybody, we tried, who knew how to make chemical rockets go. I mean, it was essentially a dead art. That we did more than our fair bit of how to rescue from the archives and turn back into practice. And the 50 or so people that we, trained in how to do that haven't left the industry. They're all out there working for other companies now. So I think we did some good, even though obviously we weren't the ones to cross the finish line.
Right.
I think it was amazing strides.
And then just you're getting the commercial launch licenses hammered out.
There's 2 years of my life I'd like to have back.
You created the industry.
Yes. I can talk about that a little bit if you want. The U.S. has been blessed at several points in its history with an uncharacteristic, and this is not the American way to do wise government policy. But at a couple of key junctures, some people got into the policy arena and pushed for wise policy, even though it was kind of ahead of its time. And that's part of why now that the commercial space transportation revolution is finally happening, it's happening in the United States. Yeah. So in the 1980s, people pushed for there to be a commercial space launch licensing regime, and for it to be, a single point of contact. So you didn't have to go around the 25 agencies and ask for permission from all of them. And none of them were empowered to say yes, but they could all say no. So that was created first by executive order under the Reagan administration, and then by the Commercial Space Launch Act of 1984 or 86. I'm not quite sure. I have to look it up. And then, when I got involved, these topics of reusable rockets and eventually rockets that carry human beings for hire, were on the horizon. And I and three other folks, were essentially the architects of what became the Commercial Space Launch Amendments Act of 1994, which was creating this kind of, I refer to it as creating just enough regulation that it occupies the space, so that people don't look at it and say, this is unregulated, therefore we have to do something. It created just enough so that there was a framework and we could add more regulation as actual practice showed that it was required. There's this idea that got very warped when people talk about it later of what's, I think, mistakenly called the learning period. I'm not quite sure when the learning period is supposed to stop. It was never intended as a life limited thing. The idea was simply, okay, rather than writing regulations based on things we imagine might happen, we should only write regulations in response to things that do happen. And when people today talk about do we or don't we extend that period, the question I always wish somebody would get up and ask in Congress during the hearings are, okay, so you believe we should move into a regime where you can regulate without any information that says that you should. Why is that? Have there been problems? Okay, if there have been problems, why didn't you use your authority to regulate when there's problems? Because you've already got that authority. If there haven't been any problems, why do you need more regulatory authority? Obviously, everything's running fine. So, but it's about time for another round of reform. The reusable launch vehicle regulations that we got in place at the time got kind of rolled back and mucked up in what's called Part 450. And now it's kind of obvious that the amount of bespoke government activity that is associated with each new launch license is way more than is required. You need some way to kind of say this falls into a category of things that we've done before. It's okay to have a lighter amount of scrutiny on it because this is not very different than the last 10 things that you did. So plus I think for those, this is getting a little technical, but the Commercial Space Launch Act and all of its subsequent amendments make the Secretary of Transportation in the United States the responsible government official for licensing a launch, not the FAA. So what happened is under Clinton, by executive order, the Secretary of Transportation delegated or was instructed to delegate those responsibilities down to the FAA, which notionally, but not in practice, reports to the Secretary of Transportation. So that was, at the time, there was hope that maybe a little bit of it's transportation, not ammunition mindset would rub off on AST. In practice, that hasn't worked out very well. And the FAA is a much larger bureaucracy that has been more impediment than help. I fully expect to see that either by legislation or executive order sometime in the next 4 years, you'll see the Office of Commercial Space Transportation move back out of the FAA, which will present an opportunity for us to revisit some of this regulatory structure.
Got it. Interesting. I got a couple questions. You ready for those?
Yes.
Okay.
And Cliff is here too.
Yeah, I did, Cliff. So Alex says, could you please tell us about sending energy to rockets? Your research in that area.
I can. Although obviously that's the technical day job, so there will be limits to what I can say. So just taking a second to compose how to answer that in a not too technical way. As mentioned earlier,
this is a crowd that likes technical. So
okay,
don't be too shy.
There's technical and then there's technical. But,
yes, exactly.
We will not be reviewing Maxwell's equations in this.
Thank
discussion. You. Okay, as mentioned earlier, in transportation, it's much more about markets than it is about technology.
Yeah.
So if it turns out that there's, a market for hundreds or thousands of Starship-sized launch vehicles a year, that's tens of thousands or more of metric tons of payload to orbit launched per year, which is a tenfold expansion over the entire global launch market, military and civilian worldwide. If that happens, it'll be awesome. If that doesn't happen, what do we do? What I and my co-founders at Electric Sky, which is the day job, answered was we would need to access some much higher traffic volume market. Okay, it's been known, at least I knew, since the 90s when I was deciding to get into this crazy business, that if you could address point-to-point transport on the Earth, all the customers are currently on the Earth. That's a much larger market. Okay, so global space launch, again, in all of its manifestations right now, is a $10 to $20 billion market worldwide. Global air transportation is a $1 trillion market. So if you could meaningfully address the global air transport market, you'd have a giant market. And now you could fly, thousands of times. And as I like to put it, you could go to orbit on evenings and weekends, and it would be cheap because you'd use all the same assets that you use for air transport. But the reason I didn't get into that 25, 30 years ago when I was first looking at this is I can't figure out how to address that market in a cost-effective manner with chemical rockets. You have to put almost an orbit's amount of energy into the craft to get trans-Pacific distances out of a rocket. You have to get like 6,000 meters a second. So you're talking about vehicles that have mass ratios not very much better than orbital rockets. So instead of an airplane where like half of your mass is dry and half is propellant, and of the half that's dry, maybe half is payload. You're talking about vehicles where a few percent of the takeoff mass of the vehicle is the payload. And it's true the propellant isn't super expensive. It's not like that's why going to orbit is expensive. Going to orbit is expensive because it takes $1 billion to keep the doors open on the company. And if you only launch 10 times, they better cost $100 million each. But when you start talking about competing with Boeing and Airbus for carrying passengers around the world, the cost of propellant really does matter. And if you're burning, twice the propellant per unit of mass that you send, and if you only get 1/10 as much of your mass as payload, your ticket price is going to be 20 times bigger than it would be if it was. Now maybe it would only be 10 times bigger, but the history of air transport has been. You look at things like Concorde.
Yep.
You look at things like the people who've tried to start all first class or all business class airlines. And ultimately, it's the low-cost carriers, not the high-cost carriers, that win. So,
interesting.
The long story short, I've had this thought for 30 years that going to point-to-point transport was the right market. And if you could address point-to-point transport with a technology that also let you go to space, then we could go to space for not very much more than the cost of air transport. But my conviction was and remains to do that. You have to be able to do high-speed transport and compete directly on price. As I put it, if you tell people, would you like to go to Japan in an hour? They all say yes.
Right.
If you say, how much more would you pay? They backpedal. But if you say, well, I could offer it for you for the same price. Now, would you rather take 13 hours or would you rather take an hour? It's not
easy.
a tough decision.
No.
So the only way I could find to do that was, so Electric Sky started when my co-founder and now CEO, Robert Millman, he kind of had come to the same conclusions independently. We met up and he was like, but, tell me how we can do this. And I said, you can't. There's no way to do it because of these issues I talked about propellant mass fraction and propellant cost and all the rest of those things. And then he essentially started the company when he called me up 2 weeks later and said, okay, I've absorbed all that. I think you're right. I've accepted all the things that you told me, but if you were going to do it, how would you? And then I said, this guy knows how to motivate me.
Nice.
So the only thing I could figure out to do was get the energy off the plane. Right. If you don't have to increase the amount of mass that you carry, you don't have to reduce the payload mass fraction, and now, flying faster and flying slower is just a case of direct energy cost. There's not this multiplying effect of making, instead of making 50% of your ship propellant, making 90% of your ship propellant. But solving how to do that, is a wicked hard problem, right? It is not a real task, right? It's not like people haven't done this because nobody's thought of it before. So, we're charging right into what we call a 4 miracle strategy. And as my CEO is fond of pointing out, 3 makes you a saint. So this is a hard problem. But you have to be able to beam large amounts of power from the ground, which is where all the power is right now. You have to be able to do that without unacceptable environmental consequences. No frying the birds in flight. You have to be able to relay that power over the horizon, because you can't build ground stations all the way across the Pacific. And you have to be able to convert that power into thrust by pushing against the atmosphere as your reaction mass, like a propeller, but at higher altitudes. If you can do all those things, you can pencil out a ship. It turns out electricity is cheaper than jet fuel. The conversion of electricity into thrust is about close to 100% efficient. The conversion of jet fuel into thrust is only about 30% efficient. So even though you have transmission losses and things like that to deal with, you kind of go through a first order back of the envelope number on the cost drivers, and you go, yeah, I can kind of see how in principle, if all these miracles came to pass, you could figure out how to fly around at, Mach 8 or Mach 10 for the same kind of price that we fly around at Mach 0.8. Then, you'd have essentially done all the job that a first stage would do. And since you're using the air as reaction mass, instead of being these, I kind of laugh when people brag about either Starship or SLS, or the shuttle in the day when they used to. It's like, it's so big, it's so powerful. The engine's the biggest vehicle ever made by man. The engines, the turbo pumps are so powerful they can suck a swimming pool dry in 6 seconds, and all of this stuff. And I'm going, that just sounds expensive. I'm not sure why you're bragging on any of this. This is your way of saying what we're doing is really, really, really hard. And I'm trying to think of a way of doing it that is technologically hard. Once you got over it, you have a ship that would go to a good fraction of orbital speed, and it would fit in a garage. So I'm not turned on by I never have been. People used to ask me about this back when I was on the Augustine Commission. I've never been somebody who's turned on by the power and difficulty of spaceflight. It's just a transportation mechanism that we currently is what we have to get where we need to go. And I'd be glad if it wasn't big, dangerous, and expensive. I'm not turned on by the big dangerousness and expensiveness of it.
And don't forget the tin can you have to live in to get there.
Yeah, it's just a truck. I'm not all gooey about it. I wish we had a better truck. And that is not, again, to saying anything negative about SpaceX or Blue or any of the people who are working on what we have now. I'm glad they're doing it. I hope they're all successful. And then I hope I can come along 10 years later and say I have a better mousetrap, and all of those big machines can be retired to the museum.
Nice. I love that. I do have a couple questions, folks. I see them. I'm going to get to you. And Alex does have a follow-up, but Peter was here first. So let's go with Peter. I had a friend that was space engineer with Rockwell. He made tracking systems for satellites that go on space expeditions.
Good for him.
Yeah. So Alex comes back with, you mentioned some Maxwell's solutions with scientist names on Space Access 19 something. And you got to welcome Society of High Sciences.
Howdy. Yeah, I mean, broadly speaking, the Maxwell's equations, which are the equations, discovered not too surprisingly by James Clerk Maxwell, are the equations that govern the behavior of electromagnetism. And even though we've had those equations for, I think, about 2 centuries now, people are still discovering new solutions to them. It's not technically new physics, because the physics is the same physics we've had for 2 centuries, but it's new ways of doing them, new ways of using them. So what we're doing for the ground to air component of the beam, to use the fancy term, is a non-Gaussian beam. A Gaussian beam, has a kind of a profile that looks like that. The intensity is smoothly varying, and it's high in the center, and it feathers out towards the edges. And that's all fine and dandy. And if you shine a flashlight or a laser pointer, across the room, you're looking at a Gaussian beam. It's bright in the center. Well, that's all well and good, but if you start sending a lot of power, if you're in the center of the beam, the intensity is high. So if you were trying to, and people don't necessarily appreciate this, but like a Boeing or an Airbus aircraft, the power level being produced by those jet engines is like 100 megawatts. If you send 100 megawatts through the atmosphere and it's a Gaussian beam and a bird is in the center of the beam, that bird is toast. Like the solar power plants in Tonopah on the border between California and Nevada, we used to call those the Kentucky Fried Chicken plants, because the solar concentrators are so intense that when the birds fly in the intense part of the beam, they crisp and fall out of the sky. So that's not cool. So
and
our first barrier, power
is wasted on the sides of the Gaussian curve too.
Yes. So what we've done is turned that beam profile inside out. So it's like a big diffuse ring of a transmitter on the ground. And because that transmitter is spread over a lot of area, the intensity is not very high everywhere, even directly over the transmitter. And then this hollow core beam comes up and comes to a focus at the receiver. So the only place where the intensity is high is quite near the receiving craft.
Sounds like it's where it should be.
Since you spend most of your time flying at altitudes where there are no wildlife, the region down where both the wildlife and aircraft of conventional type might be, the intensity is low, and we believe not going to be dangerous. So that was the first miracle. We've got that largely in hand now. We've been demonstrating that in the lab. It works just the way that the equations say it should. No big surprise. The equations have been known for 2 centuries. But there's always a chance that you messed up your math or something, and you never know until you know. Right. So, like you say, I like to bend metal. So that part is more or less in hand, and I personally am working on the later stages of the problem, the relaying over the horizon and the use of that power for thrust. If you want to fly really fast and you don't want to get really hot, you have to fly quite high. So the challenge is not a lot of work has been done on how to push against the atmosphere for propulsion at these altitudes, because if you're burning fuel in a combustion reaction to get your power, you run out of air to burn long before you run out of air to push on. So the people haven't put a lot of work into it. I'm confident we'll get there eventually, because if you have the power, there's almost always some way to make use of it. But now I have to actually say, and exactly what is that, and how are we going to do that, and what are its characteristics, and that's what I'm working on, and in the enjoying the lovely world of plasma physics, which is for people who think that both Maxwell's equations and the Navier-Stokes equations are too simple to bother with.
Okay. I got a couple more comments for you. Well, Cliff says, I know a few people that worked on the shuttle and I guess LMB lunar module that landed on the moon. Yeah, landed on the moon. Fantastic guys down in Florida at the American Space Museum. And Society of High Sciences says, how do we feel about laser propulsion for spacecraft. That sounds like the Gaussian type again.
Okay. So everything is good for something.
Yeah.
Right. You have to be okay. So for Earth to orbit, not too interesting, because as mentioned, you're talking about quite high power levels, and you can't turn the power down, or you don't have enough thrust. You'd fall out of the sky. Right. So getting off the Earth is something you have to do reasonably quickly. So that sets power levels, and lasers cost at best about $100 a watt. So if you need a 100 megawatt laser, that's a $10 billion ground station. You ain't going to build very many of those. And as mentioned, the whole global launch market is $10 billion, $20 billion. So you're not going to build one for space launch either. Yeah. Back in the day when Jordan and Lake Marabou and people like that were talking about laser propulsion, the unspoken hope was that we would build the really big lasers to shoot missiles out of the sky, and then you'd be able to use them. You're on the vast majority of days when you're not having a nuclear war, you'd be able to use them for peaceful purposes.
Got it.
That we didn't wind up living in that timeline, so we don't have the lasers, and we don't have them lying around, and nobody's likely to pay for them. Okay, so where are they useful? In advanced space propulsion for interplanetary or interstellar flight, they could be useful for interplanetary flight as a beam-powered rocket, like a nuclear thermal rocket. You send the laser, you use it to make propellant hot, you squirt the propellant out the back, propellant goes left, you go right. And Andrew Higgins and his group at McGill University are doing work on that right now. And they're doing tests in the lab to test the direct coupling of the laser energy into heating the propellant. And the Breakthrough Starshot effort is going down another road for interstellar flight, where they're looking at building a very big laser array, a gigawatt class laser array, the aperture of which would be like a kilometer across, to directly push on a light sail to push it up to something like 20% of the speed of light. But because even with that giant aperture, you in a tenth of an astronomical unit, you're out of the beam. It don't have the range to keep going. So you have to pick up all your speed in a very short amount of distance, which is why the power level has to be so high. And, they're doing some really great work on the fundamentals. They've done a lot of great work on how you gang together fiber lasers that you can buy commercially to make the big laser out of small pieces. Wow. They've done a lot of work on the sail materials. They've done a lot of work on the stability of the sail. They're doing they've done some of the studies on interstellar dust impacts to show that they're tolerable. They're doing great work. Having said all of that, a gigawatt laser is $100 billion plus asset. And I don't think it's terribly likely that beam is going to be built anytime soon. So even though I'm thrilled that they're there, I'm thrilled that they're doing the work that they're doing, I continue to look for other cheaper alternatives, because I don't think that we're going to pay that kind of money to build that probe anytime soon.
I hear you.
Does that answer? Hope that answers your question about laser rocket propulsion.
Well, there is a follow-up.
Whoa.
Think NASA looked into laser propulsion back in the 80s for interplanetary payload.
I mean, if you dig deep enough, Tsiolkovsky was talking about, actually, it's worth saying, going down that road a little bit, now that I'm in advanced propulsion and spending all my time thinking about this, it's really interesting to me how the early workers in the field, Tsiolkovsky, Goddard, Oberth, and Esnault Peltery, if I'm pronouncing that right.
That's a name I don't know.
He's a French guy. It's not as well known today, but he wrote one of the first textbooks on astronautics. In fact, he coined the term astronautics. They all, before the first liquid rocket engine had ever been built, you could work out what its performance limits were going to be. Wow. And it was obvious by 1920s that it wasn't enough. We use them today for Earth to orbit because, as mentioned, you have to get off the planet before you fall out of the sky. You know, what rockets do really well is produce a lot of thrust per their weight.
Yeah.
So you can burn the propellant fast enough to get the job done. But once you're in orbit, and certainly once you're in Earth escape, they're really hopelessly slow for the tasks that we have. You know, this business of taking years and years to get to other planets is for the birds. So you know, what are people talking about in the 1910s and the 1920s? They're talking about using sunlight pressure from the sun to drive solar sails.
Wow.
They're before the word nuclear was known. You know, they're talking about, but if you do the calculations and you say if we could somehow harness the energy of radium, you know, you'd be able to do a rocket. They're talking about groping around for what today you call nuclear propulsion.
I didn't know it was that early. That's amazing.
Yeah, because, you know, by the time Tsiolkovsky in 1903 had worked out the basics of what you could and couldn't do. In 1903, when I'm not sure there was such a thing as liquid hydrogen on the planet, you know, he had worked out that hydrogen oxygen was one of the best combinations you could get, and here's what the performance you could get out of it theoretically would be. And yes, you could get off the planet that way, but for interplanetary flight, it's kind of sad. So, you know, and hence the whole field of advanced propulsion, which I can and have. I just got done teaching a class, spending 3 days talking about it. So I can go into that in more detail than we would want to do.
Yeah, we don't want to keep you up for 3 days. I know it's a little later there. You were interested in asking about something, weren't you? Or did he answer already?
He answered, yeah, we caught it already.
Very good.
Although one of the aspects of laser propulsion is using the laser beam itself as propulsion.
You know, that's the breakthrough starshot thing. You just use the photon pressure from the light.
Yeah. Okay.
You know, which is you know, the power is the thrust times the speed of light.
Mm-hmm.
So it's, you know, 300 million watts per Newton, which is a little spooky.
Yeah. I think the thing would disintegrate at that point, having that much power in it.
Well, that was a real concern, but that is one of the areas where the Starshot folks have been making some really good progress. They've come up with some materials that, instead of focusing on making the material highly reflective, they're dielectric materials so that they only reflect like half the light, but they absorb like 1 part in 10 to the 5th of it, instead of like a metallic sail, which might reflect 90 or 95% of the light, but would absorb 1% of it. Because if you absorb 1% of it at those power intensities, you are a puff of smoke. So they're now today those materials are made on chips, you know, in samples the size of my little fingernail. And you need to be able to make them and deploy them in space on sails that have radii of meters. So I wouldn't say it's not ready to start this next Tuesday, but, you know, in terms of the fundamental barriers of is it even possible, they have found some very promising avenues for how to make it possible. Yeah. But, you know, that's enough about laser propulsion in my view, because there's much more interesting things to do.
Well, you do have another question. Let's see what he says. Could laser ion channels be used in space to steal the electrical charge from storm clouds and induce current into the spacecraft if there were 2 channels, creating a difference between Mars and Earth?
Storm clouds.
Okay, so you kind of crossed 2 streams there. I'll try to address. I'm going to use that as a springboard for talking about 2 different things. Hopefully, it will answer the question. On. There is an electric field that runs from the top of the atmosphere to the ground.
Right.
You know, the solar wind. The Earth doesn't collect the ions and the electrons at equal rates. So there's a net flow of charge that keeps the top of the atmosphere charged.
And is that why we see the aurora? It sounds like that's...
No, that's why you see lightning.
Okay.
Ultimately, what happens is the atmosphere is insulating, and eventually those charges get concentrated by air currents and they get attached to water droplets, and enough charge builds up in a local area that the insulating properties of the air break down, and you get lightning. But if people don't think about it much, but it's like, okay, after the lightning's done, how come you ever get another lightning bolt? Because somebody must be rubbing the silk on the glass rod somewhere to get the charges to build up again. And the answer is that happens up at the top of the atmosphere. So there is an electric field. You can harness it, but the energy density for it is quite low. It's not propulsively useful. If you could harness it, you would deplete it. On the scale of the planet, it adds up to a lot. There's always a thunderstorm somewhere on Earth, but there's not always a thunderstorm in the same place somewhere on Earth.
Right.
And the conductivity of the ionosphere, when you start talking about moving actual power through it, it's conductive for the purposes of reflecting radio, but it's a pretty good resistor for the purposes of conducting power. So you can't share the charge globally over the whole planet. For interplanetary stuff, no, you can't just connect the planets. They're more or less at the same potential. But it leads directly into something I have been working on, so I'll talk about that, which is one of the interstellar propulsion concepts that I and others have published is a different kind of beam, right? I mentioned one of the challenges with the laser is it's kind of short range and it's kind of expensive, or quite expensive. And if you could stay in the beam for a much longer distance, you wouldn't need as much power to pick up a given amount of energy. Energy is power times time. So a longer range beam would solve a lot of problems. And it's long been dismissed rather quickly in the literature that you could use charged particles as your beam, because people have said, well, if you run a charged particle beam, all the charges would repel. If you send like a beam of electrons, the electrons will all repel each other, which of course is true. And then they say, therefore, the beam would blow up immediately, and it wouldn't be of any use, which of course is false. We send charged particle beams through particle accelerators every day. And I ran into a accelerator physicist who's done this all the time, and he's like, I don't know what they're talking about. That we send electron beams across the lab. How do you think you get the electron beam into the accelerator in the first place? So what it turns out is, one, if your beam, it's electrons are light, so it's quite easy to get them very close to the speed of light. As you get them very close to the speed of light, from viewed in the laboratory frame, their time is slowing down. Or another way of saying the same thing is their momentum seems to go up. Or as we used to say 60 years ago, it looks like their mass has increased. So their effective charge to mass ratio gets smaller and smaller and smaller as they get close to the speed of light. Or put another way, in the frame of reference of the electrons, yes, they're all repelling each other, but they don't have any time to spread out because their clocks are moving very slow. So that's one phenomena. Another phenomena is space is not completely empty, right? There's a charged plasma in the form of the interplanetary or interstellar medium. So if you run a beam of electrons down it, they're all negatively charged. They expel the background electrons from the region that they pass through. The electrons are already present in space, and they leave the ions, which are heavy and move much more slowly. So now flip your brain around. You're now back in the frame of reference of the electrons moving along at close to the speed of light, and what they see is a stream of positive charges coming at them, which are the uncompensated background charges of the space plasma. Well, that in their frame of reference, that moving current creates a magnetic field, just like all the currents, currents in a wire, a magnetic field around the wire, and that magnetic field tends to compress the electron beam. That's called a pinch. We see this in nature all the time. We see astrophysical jets of charged particles that go across hundreds of thousands of light years out in space.
Mm.
In closer to home in the solar system, the interplanetary magnetic field is carried by what's called the interplanetary current sheet, which is a two-dimensional pinch, a pinch into a plane. And it's a current flow that runs from the sun, from the equatorial regions of the sun out to the edges of the solar system.
Oh.
And it's, on the scale of the solar system, it's only 10,000 kilometers thick, which is pretty thin. I mean, you talk about something the size of the solar system.
Mm.
So we know this pinch physics work. We use it in laboratories all the time. There are many unknowns. There are instabilities that you have to check, and we haven't checked all of them. There's challenging issues about how you start the beam. It's easy to see. It's easy to say. Once the background electrons are expelled, you have this what's called an ion focusing channel. It pinches the beam. But how did you get there from here? When you started, that channel wasn't formed yet. So there's lots of work left to do. But the upshot, which is in the published paper, is we checked the most obvious things that might be a problem. And none of the most obvious things look like they were going to be a problem.
Is that, can they find that here?
They could find that paper. It's called Sunbeam. Which is a term I stole from Doc Smith. And what it looks like is if you run this relativistic electron beam in the pinched regime, you can carry it out for like 1,000 astronomical units, whereas the laser beam is like 1/10 of an AU. And anytime you're talking about 10 to the 5th improvements, my attention has been drawn. And then it has to be done in space. You can't punch these beams through the atmosphere. So the question becomes, where do you get the power? And the other part of the paper was the realization that if you move the transmitter rather close to the sun, where the sunlight is quite intense, you can collect that power by suitable techniques. In this case, a thermionic emitter, which is two foils next to each other.
Okay.
An object that you could imagine launching, something that have a mass of like 10 tons, you can collect a gigawatt. And a gigawatt beam over 10,000 astronomical units of distance will push, a tens of kilogram spacecraft, a probe, up to close to 10% of the speed of light.
Wow.
But again, this is very early days. Don't take it to the bank. No market
for it.
What we've done is expose that this class of power beaming for deep space applications of relativistic charged particle beams, which has been kind of dismissed by inspection, probably shouldn't be dismissed by inspection. We should look at it more closely, and if it has fatal flaws, we should find out about that. Because we try looking at the obvious problems, and the obvious problems don't look that problematic. But there may very well be non-obvious problems. Welcome to the world of plasma physics. You never know it works until you've actually tested it.
So I did share that link into the chat.
And that has also a lot of my other interstellar papers.
I think there's 24 of the papers you wrote. That was the number I saw on that.
Okay. Far be it for me to quibble with your totaling of the papers.
So we did get a couple more comments in. Cliff says the Interplanetary Society wanted to use hydrogen atoms fired out and hit by a laser, an atomic explosion, but just a puff over time. 40. I'm not sure.
40%.
I think you might have been, since you were 15, you can easily be forgiven for this. I think you might not have the numbers that you're remembering quite right. I think you're talking about the British Interplanetary Society's Daedalus study. Was it Daedalus or Icarus? One of those two. That was, it was a laser or particle beam initiated fusion rocket. And you sent little pellets of hydrogen out, or deuterium, zapped them, fused them, what today we call inertial confinement fusion. And the expanding puff of plasma pushed on the base of the spacecraft. Exhaust velocity of that is, they they were a little optimistic. The BIS, by the way, if you don't know them, they're a great organization. They've been around for since the 30s. They did some really pioneering work on how we might go to the moon 20 years before we actually did. And they did one of the serious, that what he's referring to, I believe, is one of the first serious studies of what interstellar spacecraft might be, how it might be done. So that was great work. I have those reports on my shelf. They're worth reading. And I'm full disclosure, I'm on the board of advisors of the British Interplanetary Society. So we now know, or at least strongly believe, that it's very difficult to get close to 100% burn up on a fusion fuel pellet. It's true that under the right conditions, which we have now achieved, by the way, in the lab, we did ignition for the first time either this year or late last year in the well-named National Ignition Facility using the same method, but the laser zapped the pellet. And for the first time, we created a self-propagating fusion burn on a less than H-bomb scale. And the way it's done is you compress it really, really fast. So the outer layers of the pellet are squeezing the inner layers of the pellet while the inner layers of the pellet are heating up and trying to pull themselves apart. That's the so-called inertial confinement. But the consequence of that is the outer layers of the pellet don't burn very well, right? The hot parts on the inside. So it's very difficult to get, the more than, we haven't done anything, that pellet had a negligible fraction of it burned. But even if you look at very favorable conditions about what we've done on a much larger scale with fusion weapons, H-bombs, we rarely can approach more than about 25% burnout. So that means the exhaust velocity is diluted down by the inert mass of the unburned propellant. And so in practice, it's very difficult to get more than about 5 times 10 to the 6 meters per second, or what a American rocket guy would call 500,000 seconds of specific impulse.
Sounds like a good thing on the terms of bombs, and could be better thing in the terms.
Yeah, it sounds like a big number, but 5 times 10 to the 6th, is compared to 3 times 10 to the 8th. So 5 times, even if you say it was 6 times 10 to the 6th, that's only 2% of the speed of light as exhaust velocity. So in practical terms, it's difficult to get more than about 5% of the speed of light out of a fusion rocket, which might be useful as one stage of a multi-stage accelerating system. I think it's fabulous work, and I'm thrilled that people are working on it. And there's actually being some progress. There's a couple of companies working on fusion rockets of less ambitious character for merely interplanetary applications at this time. And I wish them all good things. But we probably aren't going to get to 10% of the speed of light that way. And that's kind of my threshold for it's time to go. I can imagine launching a mission to Alpha Centauri thinking we'll get the data back in 40 years. I can certainly imagine launching a mission to Alpha Centauri saying we'll get the data back in 20 or 25 years. I don't think we have to wait till we can do it in 5. That would be crazy. But doing it for a century is probably silly, because if you wait a little while, you'll be passed by the next faster ship.
Right. All right. So we got a couple more here. Do you think with the advent of metamaterials paired with a high power nuclear reactor could build up enough energy to warp space-time around the craft for a few seconds in a large capacitance dump? That is a lot of
There's a lot of technical. Some of that is technical questions, and I'm afraid some of that verges on technobabble.
I see.
Okay. I'm going to talk about it anyway, because I'm sure there are other viewers who have questions like this in their mind. You can't talk about interstellar propulsion without talking about warp drive. Okay, let me first and most importantly say we don't need it.
That's controversial.
We have already found I and others have already found over the last 10 years propulsion systems that use physics as we understand it already that can get you inexpensively up to 25 or so percent of the speed of light.
Wow.
Which is good enough to get to the nearer stars. And there's no reason to think we're at the end of this road. You know, I won't be happy until we can get that number up to 50%, and we're not out of ideas. You know, so there at 50% of the speed of light. You know, I have a chapter waiting to be published in a forthcoming book. I won't walk you through the whole thing, but at 50% of the speed of light, you know, an 11 light year jump is something you can do in a 1-generation ship. You know, you don't need a multi-generation ship to do it. You know, the some of the people who boarded that ship will still be there when the ship gets to its destination.
Mm-hmm.
You know, they'll be older then, but so I won't walk you through all the numbers, but at about 11 light, when you can do an 11 or 12 light year jump, you can colonize the Milky Way. You know, slowly, you know, you jump to another star, you settle there, you build up a new civilization, and another couple hundred years later, you send out another ship to settle the next farther star. You know, but in a million years, we filled up the Milky Way that way. You know, so it's, on the one hand, it's a mistake to think of faster than light travel as this thing we absolutely have to have if we're going to fly interstellar flight. Okay, having said all of that, obviously it would be nice.
Yes.
The plus, I don't have any answer for what do we go after we fill up the Milky Way, if we can't solve the FTL problem. How are we doing on time? Not okay. Well, okay. Any FTL system, however done, has to confront directly that if relativity is right, you know, in allowing faster than light phenomena to exist makes causality really complicated.
Mm-hmm.
That doesn't necessarily mean it's wrong. You know, there are perfectly respectable physicists who've published papers on how could causality work in that kind of environment. It's not true that it's not true that we know we can't do it. It's also not true that we know we can do it. So it's possible that FTL can't be made, is physically impossible. It's also possible that it is possible. Warp drive is now a respectable field, right? Since the first paper on it was published in, I think, 1994 by Alcubierre, you know, the respectable scientific literature on it has reached the point where I can barely keep up. You know, half a dozen really major papers are now being published on it every year, and, you know, 30 or so smaller ones looking at little bits of the math of it.
Yeah, we had an amazing guest a few months ago talk about.
Okay,
that was Greg Hodgen.
Okay, but having said all of that, the engineering of it, we can't begin to talk about how one might do it yet. We simply don't understand the physics of it well enough to meaningfully engage the engineering question. FTL requires very strange space-time stresses to be set up, if it works at all. Those stresses are not going to be achieved without manipulating energy in ways that are not for the civilizationally faint of heart. You know, we won't know until and unless we get there. But I think it's not a very good bet today to look at warp drive and say, if we had it, it would be a lot cheaper than going slower than light. And cost matters. You know, it controls what you do. So I follow the literature. I'm intrigued by it. I'm thrilled that people are working on it. I think about it too. But I think about it, and then I say, you know, until we got to the point where we can do some kind of laboratory experiment that even shows if it's a thing, there's a limit to the number of hours a day it makes sense to spend thinking about it. I should go back and figure out how to get from 25% of the speed of light to 50.
Yeah, yeah, and there are people who argue that you can use warp drive to go at slower than light speed.
Yes.
And so instead of spending impossible amounts of energy to do it, you just spend astronomical amounts.
Yeah, merely ludicrous amounts of energy are required.
Yes.
No, that was a great paper that was published, I think, just last year, Bobrick and Mateer, on I think it called it physical warp drives. Physical, as in, and the nice thing about those is there's absolutely no reason to think that there's any law of physics problem with doing that. You know, it doesn't confront the relativity time problem. It doesn't require exotic energy states. Furthermore, there was another paper that even that what's sometimes mistakenly called negative energy is even that is required for faster than light is currently controversial, because also last year or the year before, a guy named Lentz published a brand new class of warp drive geometries that were unlike anything anybody had published before, that doesn't require negative energy. And then Bobrick and company published another paper that said actually it does, and then Lentz published another paper after that that said actually it doesn't. So the subject is currently not settled.
Tennis. Okay. So Cliff had a comment, and I'm trying to remember what he was. I guess it was going to be huge. What was he talking about?
He was talking about the laser fusion.
Okay.
Oh yeah, yes. That was like a 1,000,000-ton spacecraft. Which we are not. Scoops don't work. I'm sorry to burst your bubble. I refer to the Bussard ramjet concept as an incredibly inspirational failure. The whole field, which I am working in and others are working in, on interacting with space plasma beneficially for propulsion, pushing on the plasma, drawing energy from the wind of the plasma, you know, using the medium in space for propulsive purposes, all descends from the Bussard ramjet.
Oh.
But the way it descends is Bussard had this concept of we'll put out these big magnetic fields, and they'll scoop up hydrogen in space, and we'll fuse it, and we'll make thrust. So among the fatal flaws with that idea, one of them is you can't do hydrogen fusion, and hydrogen atoms are what you scoop in space, unless you have something like the mass of a star to do it with, because the hydrogen fusion process is incredibly slow. Stars don't actually make very much energy per unit volume; they just have a lot of volume. So or they make very little energy per unit mass. So there's really no there. But the other fundamental problem is magnetic fields don't scoop. How can I say this simply? Okay. Because space plasma is very thin, any way of interacting with it requires you to manipulate it with electric or magnetic fields that are dimensionally large compared to the ship. Right, because there's only like an atom per cubic centimeter. So you want to scoop some meaningful amount of mass, the fields have to be huge. And if you made the field, by making the coils or whatever it is equally huge, the ship would be so heavy that you'd need more mass, and the design would never close. Okay, so the problem is, there's this way of describing any field in spherical harmonics. There's the first thing, which is just a spherical charge, and there's the second thing, which is called the dipole moment, which is like, what if there's a charge that's positive on one side and negative on the other side, and then there's the quadrupole moment of what if there's two charges that way and two charges that way, and octupole, and so on. You just keep going up. Okay, but the higher order fields, higher order harmonics, die out more quickly with distance. So any magnetic field when you're a long way away from the coils, just looks like a dipole field. No matter how complicated you make it. When you're up close, it can be as complicated as you want. But if you zoom way back, all you see that's left is the dipole component. And dipole magnetic fields don't scoop anything. They scatter things. Unless the particle comes in right on the axis, in which case you are going to scoop it without the scoop. So look at the Earth's field. The Earth's field does not scoop up the solar wind.
No.
It's a dipole field. The solar wind blows around the Earth. That's the way dipole fields work. So you can't scoop squat with a magnetic ram scoop. It just doesn't work. There's no there. But then what happened is Zubrin was trying to figure out, or Andrews was trying to figure out how to make the scoop work. He couldn't make it work. He sat down with Zubrin, who made a model of what would happen if he tried to make it work.
As in Bob Zubrin or somebody else?
Bob Zubrin and Dana Andrews. Thus was the magnetic sail invented, because what they discovered is it doesn't scoop anything, but it makes drag. Drag is useful propulsively. How else do you stop? And what is a sail other than a drag device being blown by the wind? And from the drag devices, then I come into the story and say, okay, if you had a drag device and you could inflate it and let it be blown by the wind and deflate it, and inflate it and let it be blown by the wind and deflate it, the wind is doing work on the sail, okay, which is a way of extracting power from the wind. Or if you have power, you can reverse that story, and you have an oar. You can push on the surrounding medium by putting power into it.
Yeah.
Or if you extract power from the wind, you can use that to expel reaction mass. Now you have a wind-powered rocket. Or you can extract power from the wind in the direction where the wind is blowing, and push on the wind sideways, which is the direction where there is no wind speed. And what do you call a device that takes power from the wind to push on the wind perpendicular to the direction of flight?
Tacking.
Like a sail.
It's called a wing.
A wing.
Okay, so now you can do lifting flight, and if you can, and then Andrew Higgins and his group up at McGill were like, if we could do lifting flight, there's wind shears in the solar system, like the one at the edge of the solar system where the heliopause is, where there's regions of space where the wind speed varies, and if you move back and forth between them, you can pick up energy from the wind on every pass, what's called dynamic soaring. And now we have a way of getting up to 2% of the speed of light without spending any propellant.
Got it.
So that whole field, all of this work descends from the Bussard ramjet. Even though the Bussard ramjet didn't work, it kicked off the entire field of realistic interstellar spaceflight.
Wow. That's amazing. I've got Society of High Sciences has 3 things here. I kind of want to run them because they're a little bit, I think they're associated. I feel like I'm getting him to tell us secrets. And with a warp drive,
if I'm shouting it to the world as loud as I can, it's not a secret.
It's not a secret. With a warp drive, you should be able to shift the magnitude of space in the dilation bubble to where you can go extraluminal without breaking the speed of light outside the bubble. Let's show this other one too. And
okay, so I can deal with that one quickly.
Okay,
that is warp drive.
Okay,
and it's both true and false. Yes, you don't ever have to move a vehicle in the space that it's in faster than the speed of light in that space. That's what makes the warp drive concept work. So you don't have the problem of, your mass goes to greater than infinity and things like that. But if any phenomena, communication, travel, whatever it is, if any phenomena that can carry information moves faster than the speed of light as seen in the rest frame of the exterior observer, the laboratory frame, you introduce this problem that either that means that motion isn't relative, or it means that causality is a problem. In other words, you can create apparent paradoxes that you have to have some way of resolving. So you can't, no matter how clever your means of moving faster than the speed of light is, you still have to confront that problem. Now, we don't know that it's a problem, right? That's why I say we don't know that these things are impossible. People sometimes say things like that. They say, well, that would mean that you would violate, that there'd be time travel, and we know that's impossible. Well, it doesn't necessarily mean that. It means causality is more complicated. But that is warp drive, and you can't make the problems of it go away by however cleverly you achieve your local mechanism. If there is a problem, there's still a problem, and if there was never a problem, there still isn't a problem.
Right. Yeah,
okay, what was the next part of the question?
Faster than light. Yeah.
So, well, and then Society of High Sciences comes back. So you could technically make bubbles in bubbles where the velocity is compounded, but never breaks the initial speed of light.
See above discussion.
Yeah. Well, the one place where it could work, where you get quantum effects, is if you were to make the bubble from the launching point to the destination. That's
a Krasnikov tube.
Right. Yeah. And that's a little expensive.
Yeah.
All right. So society comes back with all the hysteresis cycles or reality are paradoxes. So that'd be nothing new.
We are about to leave the domain of science into the realm of philosophy, and I have nothing useful to say about that.
Got it. And Alex comes back with, it's known that atomic same spin hydrogen can be stored in magnetic fields which are of achievable today's strength. Is there research on propulsion using such a fuel?
Okay, this is the old favorite, the Heinlein favorite, monatomic hydrogen, single H. Okay.
You could come back, Jeff.
That's okay.
Okay.
Okay. There's no question that as far as chemical energy goes, atomic hydrogen is basically the ultimate theoretical fuel, because the energy is, the energy that you're getting is the association bond energy of two hydrogen atoms coming together to form a hydrogen molecule, which is a high energy process. You release that energy, and your exhaust is hot hydrogen, which is about as light as you can get. So you have lots of energy per unit mass and a nice light exhaust species. It's not by accident that Heinlein and people like that thought, well, that's my perfect science fictional fuel, because it would be such wonderful stuff.
And Alex says sorry.
No. These are perfectly fair questions. There's no such thing as a silly question.
Great.
So the problems are, and this reaction instantly is used, right? This is what's called the atomic hydrogen cutting torch. You run hydrogen down a tube. You have a plasma discharge that dissociates the hydrogen, and then it recombines when it hits the surface that you're welding, and you get the very, very hot torch at the point. It's useful for things where you have to weld at such a high temperature that a normal combustion reaction will not get you there.
Interesting.
So this is not theoretical, but unfortunately, in order to, it really wants to combine. So storing it in the atomic form would require a combination of like the highest magnetic fields that we can make in the laboratory, which is not the kind of thing you normally think of as portable, and extremely low temperatures, because even the slightest little bit of thermal jiggling around will break the spin locking, which what you're doing is saying the hydrogens, when they bond, prefer to bond like this. By putting it in a strong magnetic field, you're making it more energetically favorable to stay like this, which is not the bonding direction. But a little bit of thermal jiggling means there's some part of the population that's on the other sign, and they will start to bond, and it will get hot, and the whole reaction will run away. So
Sounds like a bomb.
Yeah, it's a bomb.
Well, I mean, all monopropellants are bombs. The hydrazine is a bomb. It's just a bomb that we've learned not to set off. So but yeah, it's a spooky thing. And when you start looking at the what that might weigh and the absurdly low density of the stored propellant and how large the propellant tanks would have to be in real life, it just doesn't look like it's leading anywhere practical. We have better ways of solving all of these problems. We have better ways of solving the Earth to orbit problem. And once you're in space and you don't need the high accelerations that we associate with chemical rockets anymore, we have a whole host of methods ranging from nuclear thermal to laser powered to solar sails to, I mean, tell me where you want to go. I'll give you a better way of getting there.
Yeah. It sounds like
nice.
By the time we got to the point where we could actually do it, there'd already be better solutions.
Yes. And while I'm on the subject, I may as well also dismiss the other one that always comes up when people write science fiction, which is metallic hydrogen. Metallic hydrogen doesn't stay squoze. We've made it in the laboratory now, and as the pressure required to keep it is so high that the creep of the diamond anvils that we're using to squish together to get to the conditions where you can make it, you can't even keep it in a diamond anvil because the pressure is so high that the diamond flows and relieves the pressure, and it's not metallic hydrogen anymore.
Whoa.
So it was hoped in the 50s and 60s by science fiction authors mostly that maybe there'd be a metastable form of metallic hydrogen that we could keep around at some useful conditions. It was a fine thing to hope for, but it doesn't exist.
All right. So Janie said that keep on keeping on, Mr. Greason. Blessings for a safe, healthy Thanksgiving week, everyone. She is going to work on the Rose Parade.
Cool. It's been a long time since I lived in Pasadena, but have a good time.
Yeah. Janie's been here most every week for a very long time. All right. So, Jeff, thank you so much for everything. It's been fascinating. I'm probably going to want to see the show again, especially with a few classes under my belt.
I tried not to keep it too technical, but
it was fantastic. And as you saw, the questions were keeping up with you, I think.
Very good. Very good. Well, I hope your audience found it useful, and thanks for having me. And I would just close by saying, I came into this whole industry from a very non-traditional background, and there's lots to do. And if this is your passion, you can find a way.
Oh, yep. Great chat. And thank you. We do have a little bit more to go for people. So if you don't mind just hanging around, Jeff, in case somebody has a question real quick at the end. Go ahead, Jeff. You're up.
Okay. This Jeff.
This Jeff.
Some stellar events this week, November 22nd through November 29th. On November 22nd, the next Globe at Night project begins. These projects last for 10 days and involve observers all over the world. You essentially go out, take a photo with your phone of the night sky, use their app to compare it with other photos of the night sky to see how dark the sky is, and it helps them create dark sky maps. The project goes from November 22nd through December 1st, and you're looking for Pegasus in the Northern Hemisphere and Grus in the Southern Hemisphere. It's always Grus in the Southern Hemisphere.
Lately. Yeah. It changes.
And on the 22nd, it's the last quarter moon. Also, Regulus is 2.7 degrees south of the moon. November 25th, the moon is on the equator and is at descending node. And Mercury, well, it says Mercury is stationary. Mercury appears stationary.
Yeah.
Also, there's another meteor shower. There are 4 in November. This one is called the Andromedids, and it peaks around November 25th through the 27th. And best to observe after midnight. The peak rate is only 5 per hour, so it's not really great. Bella is the cometary source.
I think it's Biela.
Yeah, Biela.
This time the moon is good because.
Oh yeah, it's 24 days old, so it's just a thin sliver.
So the better meteor shower had a bigger moon, and this.
And it rises late, so you can actually view it at a decent time.
Yeah, I think so. Yeah.
Okay, November 26th, the moon is at apogee. November 27th, Spica is 0.4 degrees south of the moon. Now, every time it's been less than a degree, they've talked about occultation. This time they don't. So
There's got to be an occultation somewhere.
Yeah, probably.
Oh.
Oh,
A couple more comments.
yeah. Hey, thanks, Seth.
Yeah, are you here? This one?
Yeah. November 28th is Thanksgiving Day here in the U.S. November 29th is our Friday night show. Since Thanksgiving is the day before, we'll be here, and likely it will be a short episode.
Yeah, I'm thinking we'll do a holiday hang or something.
Yeah. So find us Fridays at 9 p.m. Pacific time on the Everyday Spacer Facebook page and the Everyday Spacer YouTube channel.
What inspires you the most for the coming week? And as usual, if you or someone you know has done something interesting involving space exploration, science, or astronomy, we'd love to share our live. Join us again next Friday, November 29th. We'll look for you and talk about what we're grateful for, and we'd love to hear from you as well. Thanks so much, Jeff. Jeff Greason. We really appreciate you being here. We usually do a shout out. Cliff, Scott, Alex, Society, Janie, Dawn was here. Did I get everybody? I think I got everybody.
So. Yeah.
And 2 Jeffs. Thank you so much, folks.
Peter.
Peter R. Yeah. Have a great week, folks.
Yeah.
And happy holidays if you're in the United States.
Yeah.
So, alrighty. Thanks so much. Oh, you got another one?
Yeah.
Oh, good. I'm glad you saw that.
Good night.
Alrighty.
Oh,
Good night, everybody.
So,
where's the button? There it is.
Push the button.
Yes, thank you.